One thing that we were going to come up with is that if I'm dealing at STP conditions, so I'm not changing the number of, I have a fixed number of for the pressure and the temperature, I can solve for the fact that we've talked about already that there's no special identity for gases as to what substance I have. And so I can solve the ideal gas law for the number of moles for a gas at 1 atmosphere and 273 degrees Kelvin. And I see that the number of moles is equal to the volume in liters divided by 22.4 liters per mole. So I can take a quick shortcut. If it's at STP and I'm told the volume of the gas, I know that every mole of gas at STP is 22.4 liters. So I can simply divide by 22.4 to convert volume into number of moles, but again, only if it's at STP. If I just want to, if it's at reasonably close to STP and I just want to get a ballpark estimate of number of moles, I could still sort of approximate it with that. But this is only going to be working. But if we see an STP problem, this can make the mole conversions a little bit faster than plugging in the ideal gas whole formula to try to solve for the exact number of moles. So here we go. We've talked about stoichiometry with solids. We've talked about stoichiometry with solutions, and now we're going to talk about stoichiometry with gases. And just like we saw with solutions, the only thing that changes is in step 3, if I'm given information about a substance in terms of its temperature and volume and pressure, and I need to convert to number of moles to do my stoichiometric ratio step, I can use the ideal gas law. And similarly, when I get to step 5 and I've determined the number of moles of my unknown substance, but instead of asking me for how many grams are produced, or instead of asking me for what's the molarity of the product, it might ask me for the volume or the pressure or the temperature of the product if it's a gas. And again, I can use the ideal gas law to convert to the appropriate units. So same set of steps. We might use the ideal gas law to deal with the moles in steps 3 and step 5. Again, remember, the stoichiometry problem steps start with always beginning with a good balanced equation. Don't skip that step. It's amazing how that can get you in a lot of trouble. Then we really need to sort of identify from the problem what are the given substances and what is we're trying to find. Note that in these gas stoichiometry problems, we now have not just one variable, mass, like we did in the first type of problems, or two variables, volume and molarity, but we have volume, temperature, and pressure. So we have a lot more variables that we have to worry about. And so it can be a little bit confusing to figure out what is the given substance and which one we're trying to find. And then in steps 3 and steps 5, that's where we're going to possibly see the use of the ideal gas law. This is just kind of reminding you, like, there's a variety of ways we can get to moles or get out of moles in step 3 and step 5. I can use a variety of different kinds of conversion factors. The one thing that is constant about all stoichiometry problems is there's going to be a coefficient mole ratio, my mole to mole ratio. That's the step 4 of my steps, and that's going to be common to every single stoichiometric problem. And I might have no conversions if I'm given moles, or I may have to convert from pressure and volume and temperature, or from molarity and volume, or from density and volume to grams to moles with a molar mass. So the conversions may change, but the general concept of a stoichiometric problem is going to stay the same. So here's an example of a stoichiometric problem. How many grams of hydrochloric acid is needed to produce 224 milliliters of chlorine gas at 27 degrees Celsius and 750 millimeters of mercury? And again, I know that this is going to involve stoichiometry because they give me a chemical reaction and it's asking about a quantity of HCl, but it's giving me information about the chlorine gas. So I have two chemical substances related by a chemical equation, and I know that this is going to end up being stoichiometry. So I can use my steps to kind of guide me through what do I need to do. And when I get to step 3 and it says convert to moles, and I realize I have volume and I have temperature and I have pressure, I realize I can use the ideal gas law. Here's another version of this type of problem. What is the molar mass of a gas which has a density of 0.00249 grams per mole at 20 degrees Celsius and 744 millimeters of mercury? So I'm given a temperature, and I'm given a pressure, and I'm given a density, and I'm asked about molar mass. Now, remember, when they're asking me about molar mass, I know that the units of molar mass are grams per mole. So I'm thinking if I just knew how many grams it was and I knew how many moles it was, I could figure this out. So that's exactly what we're going to do. So we know from the density, which converts volume to grams or grams to volume, I can get the grams. And I know if I knew the volume and the temperature and the pressure, I could find the number of moles. So the thing that I have to do is I have to start about some certain size sample in terms of volume of a gas. And since I'm going to use a ratio, it doesn't matter which volume. I could do 100 milliliters, I could do 1 liter, I could do whatever I want. But so I'm going to assume that the volume is 1,000 milliliters, and I'm going to solve for the number of moles, and I'm going to use the density to solve for the number of grams, and then I can take the number of grams and divide by the number of moles. The last topic in this chapter is really sort of talking about the very beginning. I said there is no such thing as an ideal gas. We have gases that come close to being ideal, but we really need to know when is the gas not very ideal so that we know we're going to have problems when we use the ideal gas law, and the calculations aren't going to be quite sufficient enough. So going back to our original assumptions, we talked about the particles taking up no space, they're being point masses, and that having no attraction for one another, and having those perfectly elastic collisions, they don't stick together. So those are the two things that tend to break down under certain conditions where that's really not a valid assumption. So I want you to think about what conditions would the volume of the particles not be zero? Under what volume conditions does that point mass assumption not be a very good one? Would that be at very large volumes or at very small volumes? At which point does the volume and the size of the particles themselves start to become a noticeable difference? The other thing is the pressure. Remember pressure, let's think about that as being the number of collisions. So at high pressures, when I have a lot of collisions, or at low pressures, when I have very few collisions, when would that most have an issue of either the space being an issue or the attraction of the particles? And the last one to think about is temperature. Remember, we think about temperature as being associated as the speed of the particles. So is it when the particles are moving very slowly that I should have an issue with this, or when they're moving very quickly? Well, again, we know that if I have a gas with a large volume, then for the most part, all of the volume of the gas is the empty space between the particles. But when I start to get to very small volumes, the size of the particles themselves starts to become an appreciable portion of the volume of the gas, and so small volumes are an issue. If I have pressures that are reasonably low or a few times above atmospheric pressure, but when I get to incredibly large pressures, remember I'm pressing those molecules, they're getting closer together with a lot of collisions, and every time it collides, the fact that they aren't exactly no attraction, there is some attraction, suggests that maybe I'm not going to have those elastic collisions. And so at high pressures, I begin to deviate from ideal conditions. And when I have very high temperatures, when they're moving very quickly, that's a good thing. If I have very low temperatures and they're moving very slowly, then when they collide, they tend not to have those elastic collisions. The attractive forces, when it's not moving slow, when it's not moving fast, it's moving very slow. When they collide, they may have a sticky collision and tend to stick together because the attractive forces can sometimes win out. So I'm looking for cold, high pressure, small volume gases are not going to behave like a very ideal gas. And when I try to use these equations on gases that are under those conditions, I'm going to have a lot of error. That my calculations are going to be they're not going to be very accurate. So I should be aware of those situations.